There we go. Well, we are very excited this week to have George Nasr, a postdoc at the University of Oregon, talking to us today about matroid valuations and stressed hyperplane relaxations. Take it away.
All right. Thank you very much. Thanks, y'all, for coming and the invitation. It's lovely to give talks, Zoom or in person. Yeah, I think I just want to jump right into the talk. So let's jump right in. So I'm just going to start with an example. I'm going to start with this example where P is a collection of two-dimensional polygons, and I'm going to have this function from P to the reals defined to be the area function. So if I plug in a polygon, the function will spit out the area of a polygon. Nice enough. And this function has a pretty cool property. If I have two polygons whose union and intersection are polygons, this function f that I've defined will satisfy this property that the area of the union is the individual areas minus the area of the intersection. And if you think about some kind of picture in your head, it should be kind of nice, but here's just an example to make sure that's concrete. So here I have a 2x3 rectangle P1 and a 4x2 rectangle P2. They've got this overlap of a 2x1, and overall it's a 6x2 rectangle, and you can verify that the area of the union is indeed the sum of the individual areas minus this overlapping area. Okay, so this function f has this really nice property that it decomposes this way over polygons. And this is a property that I'm actually interested in generalizing. And so let's go ahead and generalize things. So instead of talking about polygons, I'll talk about polytopes. Instead of the real numbers, I'll just use some abelian group. And now this function f will be called a valuation if it satisfies that same property from the prior page, given that the union and the intersection of the polytopes are, in fact, polytopes. Okay, so this is what I mean when I talk about evaluation, and the area function on polygons is just one example of evaluation on functions. But I'm not just interested in any ordinary valuations. I'm particularly interested in matroid valuations. So what I'd like to do now is talk a little bit about what matroids are and show how we can connect the theory of matroids into the theory of valuations. So I like to motivate matroids in the following way. I have a pair E and script B. E is some finite set, and script B is a collection of subsets satisfying two axioms. One is that this script B is non-empty, and the other is this kind of complicated looking relationship. But what it says is for any two elements of script B, I can remove an element from one and add an element from the other and get another member of this family script B. So it's kind of giving you this relation that tells you two elements of script B can kind of swap elements in a very specific way. There are some careful quantifiers and guarantee you still get a member of the same family. Now for such a matroid, E is going to be called the ground set. Any member of script B is called a basis. And now using axiom 2, you can actually verify that all bases have the same cardinality. So I could have been a little bit more explicit with this description up here, but a priori, that was the least data I could have given. So that's why I phrased it like that. Since all bases are the same, we'll give that, or are the same cardinality, we'll call that cardinality the rank of the matroid. And finally, any subset of a basis is called an independent set. So
I'd like to ask a question. If E is the ground set, does that mean the elements of E are called grounds?
I believe
like coffee grounds?
That would be fun if that were the case. I think I think matroid theorists should try to incorporate that into the common literature. But as of right now, no, it is not that way. I love that idea.
We're looking for an opportunity then. Okay, just wondering. I'm thinking about coffee, I guess. Okay. All right, thank you. You're doing fine so far. I just thought I'd inject a little interruption.
All right, thanks. Yeah, maybe in my next paper, I'll try to coin some new terminology.
Brave man.
All right, so that's what a matroid is by definition. And at this point, you've seen the word basis and independent. And so I don't know what people know about matroids here, but if this is your first time, you should be thinking about linear algebra based on the terminology. And indeed, if I take E to be the set of columns of a matrix over some field, and I take script B to be the subset of columns which form a basis for the column space of that matrix, that satisfies that exchange relation that I showed you on the prior page. And this is a matroid called a representable matroid. And just to give a nice concrete example, which will be reoccurring throughout this talk, here is a matrix. Let's just take my field to be the real numbers. And you can verify that the column space is R3 here just by looking at columns 1, 4, and 5. I've labeled the columns V1 through V5. And you can just check that the correct choice of script B for a representable matroid here are the triples that are not contained in the first 4 columns. Okay. So that's an example of a matroid. Another specific case of a representable matroid can actually come from graphs. So graphs gives rise to matroids too. I won't define these precisely, but just for anybody who likes graph theory here, you can take E to be the set of edges of your graph, and then you take script B to be the collection of spanning forests of your graph. And these also satisfies the same axioms, and you can actually show that those matroids are representable matroids. I won't use graphic matroids in this talk, but graphs are cool objects, and so for anyone that likes graphs, I wanted to throw that in here. Okay, so that's an example of a matroid. Let me give you one more example of a matroid. So there's a matroid called a uniform matroid. Here the ground set is the set E, and R denotes the rank of the matroid, and the condition for a uniform matroid is every subset of size R is a basis. So a priori, there's no reason to expect that every set of size, remember all bases have the same cardinality. There's no reason to assume all bases have the same size. But if they, there's no reason to assume every set of the correct size is a basis, but if it is, we call that a uniform matroid. And just for an example, U2 of the set of size 4, it has the following bases, where here I've kind of suppressed the set 1, 2 as 1, 2, and so on and so forth. So these are the 6 2 subsets of the ground set 4. Bases are maximal. No, I believe spanning forests is actually correct. If you have a spanning forest, it is maximal.
No, it's not. No. Let's not get distracted. We can discuss this afterwards.
Okay. Well, at least for, okay, perhaps I'm forgetting something special in the case where it's disconnected. Definitely for a connected graph, it is the spanning trees.
No, we will discuss this afterwards.
All right. All right, well, moving on. So those are some examples of matroids. And so now at this point, you're like, okay, cool. Thanks for showing me what matroids are. But what does this have to do with the valuation stuff? Where are the polytopes in this picture? And so for that, I want to introduce the base polytope. So given a matroid M, this gives rise to a polytope P sub M, which I call its base polytope. And this is the convex hull of indicator vectors corresponding to the bases of M. So just to give you a concrete example, here is the uniform matroid of rank 2 on 3 elements. Here are the bases and the corresponding indicator vectors. So the vectors just have a 1 in a position if that element is in the basis and a 0 otherwise. So here I'm kind of taking advantage of the fact that my ground set has a natural total ordering to it. So that's how you get points associated to it. And now these are elements of R3, and I can plot those in R3. So here I've drawn my axes where the origins in this back corner, and you take the convex hull of those points, and that includes the interior of this triangle, not just the boundary itself. So that's an example of a base polytope. And now the point is we now have a way to associate a polytope to a matroid, and from here, we can now do valuations for matroid theory by talking about base polytopes instead. So that's how we get matroid theory for valuations. Or sorry, the other way, valuations for matroid theory. So great. So now I'd like to show you a couple examples of valuations that I'm going to be talking about in this talk. The first one's a pretty popular one that exists outside of the scope of matroid theory, which is called an Ehrhart polynomial. For this, I'm going to start with a few definitions. So first, for any polytope P in real number T, TP is just taking the elements of the polytope and scaling them by T. I call that a dilate of P. And now for any positive integer T, so I'm going to fix T to be positive integers now, I'm going to define this function air sub P of T to be the number of integral points sitting in the teeth dilation of P. Okay, so this function is counting the number of points with integer coordinates sitting inside some kind of dilate of my polytope P. And a beautiful theorem by Ehrhart says that when P is the convex hull of points whose coordinates are integers, you can actually guarantee that this function is a polynomial in T. So we can just do this for any polytope, but I'll point out that, remember, the base polytope satisfies the hypothesis here because it's the convex hull of points whose coordinates are 0, 1s, which are indeed integers. And thus we can define the Ehrhart polynomial for a matroid M by just defining it for its corresponding base polytope. So that's how we'll define Ehrhart polynomials for matroids. Great. So let me just give you a quick example just so you can get a feel for what these look like. I won't do it for a matroid though. I'll just pick my polytope to be the unit square. So here's my unit square and its dilates. And we can verify that air sub P of 1, just the number of integral points inside the original polytope, is 4. In the second dilate, there are 9 points. In the third, there are 16. And indeed, in general, there are T plus 1 squared, which is in fact a polynomial. So great. Now, I will point out this polynomial has a nice property, and that the coefficients are integers, and that need not be the case in general. So I didn't want to mislead anyone. I just had a nice example that happened to have nice coefficients. Okay, so that's the Ehrhart polynomial. And I didn't yet say this, but the Ehrhart polynomial is indeed a valuation, because if you think about it, the Ehrhart polynomial is basically a discretized version of computing volume, which is a general version of computing area. So if you believe my example at the start was a valuation, then I'm saying the same reasoning will help you see that this is also a valuation. So great. This is one example of a valuation. And if I specify my matroid to be, if I specify my polytope to be a base polytope of a matroid, then we get a matroid valuation. Great. So now I'd like to show you another valuation that I'll be interested in. This one requires quite a bit more technical details, but I think it's worth seeing if you've never seen something like it before. So now I'm going to talk about incidence algebras. So we're going to start with a poset P and a rank function that goes from P to the integers. And this function basically satisfies, it basically respects the ordering of the poset. So the rank of X should be less than or equal to the rank of Y if X is less than or equal to Y. Now, given a rank function for a poset, we can define the incidence algebra, which is the set of functions of the form P cross P to polynomials in T with integer coefficients, where I'll write fxy of T to denote the evaluation at the pair of points xy, and this will satisfy some axiom. So you're supposed to think of the incidence algebra I of P as a collection of functions which take in a pair of poset elements and they spit out polynomials. Now, I'm not going to mention what these axioms are. They're not so important for this talk. I just want you to have the idea of what this object is. And I will say that I'm calling it an algebra because indeed these functions do form an algebra under pointwise addition. And there's this fancy product called convolution product. I won't write down specifically what that convolution product is, but if you've heard that word before, you might have some sense to what the product might look like. And in this algebra, you do have a multiplicative identity, and some functions will have multiplicative inverses, but not all of them will. Okay, so I'm going to talk about a special type of function now, but first I will give you a way to construct a new member of I of P from an old one. So if you have a function f in your incidence algebra, you can define the barred version of f, where it's defined pointwise to be this. And so I'm kind of denoting rank sub y and rank sub x as the ranks of x and y respectively. And so this is the computation. And you should be looking at this and being not confident that this isn't the incidence algebra. In particular, we need that to be a polynomial. So you should kind of question if it is a polynomial, but that's clear from the axioms that I've suppressed. So the axioms that I've suppressed here makes it clear that this will in fact be in the incidence algebra. So I just don't want to dwell on these details because it's not really worth it for this talk. But okay, so that's the incidence algebra. And this is a new function. And now there's a special type of function called a p-kernel. So a function kappa is a p-kernel if kappa of xx is always 1 for all x, and the inverse of kappa equals to this kappa bar thing that I just defined. So your first question should be, well, how can I just assume kappa inverse even exists when I told you some functions have an inverse, but not necessarily all? Well, actually, that's what this condition is. It turns out that this condition guarantees that your function has an inverse. So that's why we write that kappa xx equals 1 for all x there. So that guarantees the inverse exists. And then kappa inverse equals kappa bar is the definition. Okay, so those are p-kernels. And with the p-kernels, we get this very interesting theorem. So given a p-kernel kappa, we can find unique elements, f and g, of the incidence algebra satisfying the following conditions. For all x, we have the same condition that fx and gxx equals 1. For every x less than y, the degree of the polynomials indexed by xy has degree smaller than rank of y minus rank of x divided by 2. And finally, the barred version of x is kappa times f, and the barred version of g is g times kappa, where this multiplication is that convolution product, which I didn't explicitly define for you. And so to this end, since we're multiplying f on the right and g on the left, we're going to call f the right KLS function for kappa, and likewise g the left KLS function for kappa. Now, where are these letters KLS coming from? Well, you may have noticed my references up here, Kazhdan-Lusztig and Stanley, and you'll notice some big time gap in between them. And so the history here is that these polynomials were originally defined by Kazhdan and Lusztig when they were studying specifically the case where P is the Bruhat order for a Coxeter group. They were studying some interesting algebra stuff, and this helped them do their work. But then later Stanley realized, hey, this was a really cool function you defined, but actually you didn't need your poset to be the Bruhat order for a Coxeter group. You could actually just let it be a ranked poset with some nice properties. And so that's why I'm attributing this kind of to both of these folks here, or all of these folks here. So that's a little bit about the history here. And so now what I want to do is focus on the case of a very special p-kernel. So let's look at this function here, zeta sub xy of t. So zeta sub xy of t is a really, really boring element of the incidence algebra. It's 1 if x is less than or equal to y, and it's 0 otherwise. So this is in fact a part of the incidence algebra. Of course, I didn't give you the axioms, so you cannot necessarily verify that, but it is in the incidence algebra. And I'm going to define a new function called the characteristic function, which is the inverse of zeta times the barred version of zeta. Now, this characteristic function under the right choices of posets can, I think, either exactly realize or get close to the chromatic polynomial of a graph, if you know that, and a lot of other important functions that arise in other settings. Now, you can verify that kappa is a p-kernel. This is hard for us to do because I have not told you how the convolution product works, but indeed you can show the inverse of this function is the barred version of that function. And so we have a p-kernel, and we'd like to know what are the left and the right KLS functions. So there's one that's really easy to compute. Notice if I multiply chi on the left by zeta, just because I have the inverse of zeta written here nicely, this is an associative operator, and we get zeta chi equals zeta bar, which is exactly what it means for zeta to be the left KLS function for chi. So the left KLS function for chi is very, very, very boring in that. And so like, maybe I should say why I think this is boring. Remember, the incidence algebra functions index polynomials, and zeta, the polynomials here are degree 0. They're not very fun and exciting. And so we wonder now, maybe the right function is more interesting. And indeed it is, but I won't study these for general posets. And this is where matroids will come back into the picture. I'm going to specifically be interested in studying these right KLS functions in the context of a poset for a matroid. So how do you get a poset for a matroid? Well, you start by talking about ranks of sets. So given any set, subset S of the ground set of a matroid E, the rank of S is the size of the largest independent set containing S. So the rank of a matroid is just the size of any basis. And then we can extend that idea to any subset by just saying, what's the largest independent set contained inside of you? And now we'll get a special type of set called a flat. A flat is a set that is maximal with respect to its rank. So that means if I add an element to the set, I increase the rank. And this gives rise to the lattice of flats ordered by inclusion. So you may recall this representable matroid I gave you at the start of the talk, and here is its lattice of flats. So what I am actually saying here is the empty set is the unique rank 0 flat. These are the rank 1 flats. These are the rank 2 flats, and E is the unique rank 3 flats. And just to make sure the definition is concrete, I can talk a little bit about what makes a couple of these flats. So why is V1 a flat? Well, V1 is already independent. It's a singleton, and so its rank is 1. And any element I add to V1 makes it into an independent set of size 2. Every tuple of vectors here are independent. None of them are scalar multiples of each other. Thus, adding any element to that set increases the rank, and that makes V1 maximal with respect to its rank. So V1 is a flat. V1, V5 is also a flat, because if I add any of V2, V3, V4, I turn this set into a basis. So again, this is independent of rank 2. Adding an element makes it independent of rank 3. I increase the rank, therefore it's a flat. V1, V2, V3, V4, V5 is actually a more interesting flat because it is not itself independent, unlike the prior two cases. It is a rank 2 flat. But it is a dependent set. But of course, the only element I can add to this is V5, which of course adds tons of bases inside of this, increasing the rank to 3. So these are different examples of flats, and I've drawn kind of the inclusions here, the partial orderings here. Okay, so that's how you get a poset associated to a matroid, and I can now define the corresponding KLS function. So let's let P be the lattice to be the lattice of flats for a loopless matroid, where loopless means every element of the ground set is in some basis on some ground set E. And let's let F be the right KLS function for that function chi that I mentioned a few slides ago. Then we're going to define the Kazhdan-Lusztig polynomial for M to be P sub M of T, and it's going to be the right KLS function, but not just the right KLS function in general. I'm going to specifically specify the one at the pair of poset elements empty set comma E. So remember, my incidence algebra functions are indexed by poset elements, and so I'm specifying I want the one indexed by empty set in E. And so at this point, you should be saying, okay, well, how do I know those things are always there necessarily? Well, E is always going to be the maximal, is always going to be the largest flat. It has rank equal to the rank of the matroid, and you can't get any bigger than it. So it is maximal with respect to rank. In general, for matroids, empty set is not necessarily the smallest flat. But if you have this loopless condition, it actually is guaranteed that the empty set is your rank 0 flat. So that's really what's important here. I will comment that if your matroid has loops, if it has elements that are not in any basis, then you are guaranteed that this polynomial is 0. I won't really say about why that is the case, but it is. Okay, great. So this is so I gave you one example of evaluation much earlier. I know we spent a few slides on this, but we talked about Ehrhart polynomials before this. That was one example of evaluation. At this point, you're like, okay, cool, incidence algebras, interesting, but why the heck is this evaluation? Over there was some nice geometric interpretation. Here, there's not. And indeed, it actually involves a lot of fancy algebra to show this is evaluation. So it is hard to prove that this is evaluation, but indeed, Ardila and Sanchez were able to show that this was evaluation in 2020. And they use some interesting higher level math to do that. So there's nothing about this definition that should make it evident that this is evaluation. But it is. So great, I have a couple of valuations now, and these are the valuations that I'd like to show you some of my results for today.
Excuse me, George.
Oh, yes.
It's a valuation on what? On matroid-based polytopes? Is that what you say?
Yes, yes.
Okay,
I only care about valuations of matroids. Yes.
Well, of matroid-based polytopes specifically.
That's what I mean when I say valuation.
Okay, I'm sorry. Yeah, I just forgot. Thank you.
Yes, yes. You can only define a valuation for a polytope. So whenever I say valuation for matroid, you should substitute that for meaning base polytopes. Thanks for asking me to clarify that. Yeah. Okay, great. So a lot of my work has been trying to find creative ways of computing formulas for valuations, specifically these two valuations, which is why I spent so much time setting up this stuff. And so what I'd like to do now is show you the technique that I developed for a very special class of matroids. And to do that, I need to share a little bit more about matroid terms. And so let's talk a little bit more about matroid theory. So a hyperplane for a matroid is a maximal set not containing a basis. So that means if I add an element, it will contain a basis, but it didn't before. Somewhat dually, a circuit is a minimally dependent set. So that means if I remove an element from it, it becomes independent, but it is not already independent itself. And just to make these a little bit more concrete, here again is our representable matroid, and here are some hyperplanes and circuits. So note that each of these sets do not themselves contain bases, but the second I add a single element to any one of these, they will contain a basis. So they are all hyperplanes, and much like you would expect for a hyperplane in general, the rank of all of these is 2, and the rank of the corresponding matroid is 3. So indeed, hyperplanes have co-rank 1 for a matroid. Here are my circuits. So remember, circuits are minimally dependent, so they are themselves not independent. You can verify that these are all dependent sets, but of course, every subset of them is independent. This isn't very interesting here. It's just because every pair and singleton is independent because I don't have any columns that are scalar multiples of each other. So those are circuits and hyperplanes. And when you combine those two things together, you get something really, really cool. A circuit hyperplane is a set that is both a circuit and a hyperplane, and it lets you do something interesting. Given a circuit hyperplane C and of some matroid, then I can add that element C to the set of bases for the matroid, and that's actually guaranteed to satisfy the axioms for a matroid. So I can construct a new matroid, and we call this new matroid the relaxation of M. So I hope this is clear what I'm saying I'm doing here. I'm starting with a circuit hyperplane. I have a matroid with some set of bases, and I'm going to formally add C to the set of bases, and that's guaranteed to also satisfy the axioms for a matroid. So this is a pretty well-established matroid theory operation, and this gives rise to a very cool class of matroids called sparse paving matroids. These are the matroids that are defined by having the property that you can continuously relax them until they become uniform. So remember, uniform matroids are the matroids where every possible set that could be a basis is a basis. That is, if your matroid is rank R, then every set of size R is a basis. So what I'm saying here is I can continuously add, or I can continuously, so I can start with a matroid, I can relax it if I find a circuit hyperplane. And the idea is if I can continue to find circuit hyperplanes and relax them, and I continue over and over and over, and I eventually end up at a uniform matroid, then the matroid I started with is a sparse paving matroid. Note that that necessarily implies that C is the same cardinality of any basis. That's actually follows from being a circuit hyperplane. And you might say, well, could I not always do that? And the answer is no. It is totally possible to find a circuit hyperplane in a matroid, relax it, but then end up with a matroid that has no more circuit hyperplanes. So it is special to have this property.
So if I understand this, you could reverse the process and say, this is a matroid obtained from the uniform matroid by tightening bases into circuit hyperplanes.
Yeah, there are some things you have to be careful with. You can't just willy-nilly pick bases to relax. You have to make sure that, you know, those axioms that I showed you are satisfied.
Okay, so reversing that is not trivial. Thank you.
It's not trivial, yeah. But actually, I'm glad you brought that up, actually, because that's actually how I discovered this operation. I started in reverse, and then I later found out that this operation exists the other way. So it is very natural to go that direction. At least to me, at least. Okay, great. Okay, and so sparse paving matroids are actually related to another matroid called paving matroids. Paving matroids have the following property. For any set whose subset of the ground set whose cardinality is less than the rank of M, we say that that set must be independent. So compare this to the uniform matroid. In a uniform matroid of rank R, every subset of cardinality at most R is independent, because if you're equal to R, you're a basis, and every subset of bases are independent. This is slightly weaker. It's saying every set of cardinality at most R minus 1 must be independent. So it's kind of the same thing as a uniform matroid, except you have not all of your size R subsets are independent, but everything lower is independent. And you can actually show that every sparse paving matroid is a paving matroid, and it's conjectured that paving matroids are asymptotically almost all matroids. There is some preliminary evidence for this, but there is not a full-blown proof of this yet. And so I really like thinking about these matroids, one, because I like the definition myself, but also because if you can prove some things for these matroids, you at least conjecturally have proven it for a lot of matroids. And so the goal of my research has been, I want to try to compute valuations for this class of matroids, paving matroids. Now, for the Ehrhart polynomial and for sparse paving for the Ehrhart polynomial and the Kazhdan-Lusztig polynomial, lots of work has been done for sparse paving matroids utilizing this relaxation operation, the fact that you can define them via this relaxation operation. And so the question I had was, well, since every sparse paving matroid is paving, can we generalize this notion of relaxations to paving matroids? That is, while sparse paving matroids can be repeatedly relaxed until they become uniform, can I generalize the idea of relaxations so I can repeatedly relax paving matroids until they become uniform? And the answer turns out to be yes, as I proved with my colleagues Luis Ferroni, who's now at KTH, and Lorenzo Vecchi, who's at University of Bologna. And we proved the following statement. Given a rank R matroid, if you have a hyperplane whose R subsets are all circuits, then you can add those R subsets of H back into the set of bases formally. And this is guaranteed to be a matroid. We call this a relaxation of H and M, and we call H a stressed hyperplane, kind of on the nose there with the word stressed and relaxation. So I just want to be clear here that if H itself had cardinality R, I would be saying that H is itself a hyperplane and a circuit, and I would only be adding that. That would be a singleton set I'm adding in, and that recovers the original definition of relaxation. So this is an honest generalization of the relaxation operation that I showed you previously.
So does this mean that H itself is a uniform matroid?
So H is a hyperplane. H is a subset of the ground set.
Yeah, but it's a matroid. It has its induced matroid.
Yes. Yes. Oh, this is what you're asking. Yeah. If you look at the independent sets contained in H, or the bases contained in H, then yes, you do get a uniform matroid.
So it's equivalent to say that H is a uniform matroid.
Yes. Yes.
Okay, thanks.
Yeah. Okay, awesome. And so this is a cool operation that we've generalized. And now the point is that you can prove that every hyperplane in a paving matroid is stressed. And thus I can go through and relax all of the hyperplanes in my matroids until I've added all the possible R subsets back into the set of bases, and thus recovering a uniform matroid. So this successfully generalizes the notion of a relaxation. It does exactly what I sought out to in this question above. Okay, so that's this relaxation operation. I've generalized it. And now let me remind you, why am I doing this? Well, there was a lot of work on computing valuations for sparse paving matroids, which took advantage of that relaxation operation. I've now generalized that operation. And so I want to see if I can still be able to use those ideas and techniques to compute valuations using this new idea of valuations. And so how do we compute valuations? Well, we need to talk about the polytopes. So now I want to talk about what's happening on the level of the base polytope for a matroid when I relax a stressed hyperplane. So here's just my setup. I've got my matroid, a stressed hyperplane, its relaxation. So when I do this, there must be a polytope P, so that the base polytope of the relaxation is P union the base polytope of M. Remember that it's been a while since we said what these definitions were, but remember the base polytope is the convex hull of these points that correspond to bases. And I'll just go back to the prior slide real quick and point out that the bases of M tilde are the bases of M along with some extra sets. So you should be thinking of this relaxation on the level of polytopes as I'm starting with the base polytope for M. I'm then adding some more points and taking a new convex hull of everything. So there should be some P that I'm really like gluing onto the original base polytope. Geometrically, it's just the closure of that difference then, but actually you can show that this polytope P is a matroid polytope for some matroid. And I'm going to denote that matroid n sub h. So h is just meant to remind you that we got this relaxation by relaxing this hyperplane h. And so I now can write this formally. So we relax, and what relaxing does is it takes my base polytope of M and it glues on this new polytope piece of n of h, and we get the relaxation, the base polytope for the relaxation. But now remember, I told you I can continuously relax. If M was a paving matroid to begin with, I can continuously relax it until it becomes a uniform matroid. And so in that case, I can just continue to glue on all these various chunks until I actually recover the base polytope for the uniform matroid. So this actually kind of gives you a way of starting with a base polytope of a uniform matroid, which by the way is a hypersimplex for those that like that object. And it kind of slices off a bunch of chunks in a way that you can witness the original base polytope. So here I'm just doing repeated relaxations to this formula here. Okay, so that's on the level of polytopes. And now I can say something on the level of valuations. And so let's say we have a valuation f, and I want to compute f of m for some paving matroid m. Now remember, this kind of ties into the question I was asked earlier. I haven't told you valuations for matroids. I've told you valuations for polytope. But in this context, what I mean is the valuation for the corresponding base polytope. So that's what I mean when I write this. And given a stressed hyperplane, using the formula we had on the prior slide, we have that this is true on the valuation. So if you remember way back to like the first and second slide of my talk, this is that formula I wrote down for valuations. M is P1, NH is P2, M tilde is the union, and this is, of course, their intersection. So I've just rewritten things around a little bit differently. But this is the formula for the valuation in the case where P1 is the base polytope for M and P2 is the base polytope for N sub H. And now using this idea that I can continuously relax until I get a uniform matroid, we can actually further rewrite this in this form. Now, there's some stuff I'm hiding under the rug here. I won't go into the details, but the point is I continuously apply this formula to this term until it becomes a uniform matroid. And then I just will have a bunch of terms that correspond to the things I relaxed. So this is meant to be in line with what you saw on the prior slide with that decomposition into a bunch of polytopes. You might be saying, shouldn't there be more intersections between different chunks maybe somewhere? But the answer, it turns out to be no. So this is the correct formulation. I've just kind of suppressed some details under the rug. So what I have done is I have used the relaxation operation in order to take any valuation of a paving matroid and express it as the valuation of a uniform matroid minus a bunch of these things. And the idea is that I can use this as a way to compute the valuation for a paving matroid. And at this point, you should be saying, okay, like even if you like weren't so happy up to now, you could be looking at this and saying, this looks way worse than what you started with. Instead of computing the valuation for one thing, I have to compute the valuation for a whole bunch of things. But it turns out that these things are substantially easier to compute than the paving matroid case. Uniform matroids is almost always one of the first example we compute valuations for. And these matroids end up being extremely nice, extremely nice. In fact, you can kind of relate them to the uniform matroid. And I've written out their bases on the next slide. I won't really talk about them right now. They're here, but I'd rather just jump finally to the results. So I can come back to this if anybody would like. But now let me show the results that I was able to produce using this idea and this formulation. So first, if C sub I of M is the ith degree coefficient of the Kazhdan-Lusztig polynomial M, then we have the following formula. If M is a rank R matroid with a stressed hyperplane H, then if M tilde is the relaxation, we have that the ith degree coefficient of M is the ith degree coefficient of M tilde minus the number of fillings of this diagram. So what this is like, if you know anything about standard Young tableau, it's the same rules. You fill the rows left to right, strictly increasing, top to bottom, strictly increasing, only using the numbers 1 through the number of spots. And specifically, I forced the number 1 to be in this location. So I kind of have a combinatorial formula here involving the relaxation. And you can see the parameters I for the ith coefficient, R for the rank, and the cardinality of H is involved here. So note how nice that is, that I don't really care how H interacts with the matroid itself. I don't care what H really looks like. I just care about its cardinality. So that's if I just want to relax, but what if I have a paving matroid and I can continuously relax to the uniform matroid? In that case, here's our setup. Let H sub j be the number of hyperplanes of cardinality j. Let M be how much larger the ground set is than the rank of that matroid. Then we have the following formula. So here we have the number of fillings of this diagram where I don't care that the number of 1 is here, minus the sum over j, recording the various sizes of hyperplanes. And we take H sub j and we multiply it by the number of fillings of this. So notice here, the size of the hyperplane is replaced by the index j. So this term is the same as the prior slide. Now I'm multiplying it by H sub j, the number of hyperplanes of size j. And this formula should be a little bit reminiscent of what I wrote down here. It's a term minus a sum of a bunch of terms corresponding to a hyperplane. And indeed, what I'm suggesting is true, that that first term I wrote is the ith degree coefficient of the Kazhdan-Lusztig polynomial for the uniform matroid. And this is the difference of those Kazhdan-Lusztig polynomials in that second term in the sum. So this is the case of the Kazhdan-Lusztig polynomial that I computed. And so that's the result for Kazhdan-Lusztig polynomials. And then we also have a result for Ehrhart polynomials. Before I show this result, I'm sure everyone's like, why are there a bunch of people on this paper? And the answer is that this was a part of a workshop called the Graduate Research Workshop in Combinatorics, which some people may be familiar with. And so lots of people were there working on different problems, and this was one of them. So in this result, we proved if M tilde is the relaxation of H and M, and S is the cardinality of H, then this is the formula we get for the relaxation. So the Ehrhart polynomial of the relaxation is the Ehrhart polynomial of M plus this term. And I know this is like kind of a crazy looking term. I understand that you're probably like, what am I meant to glean away from this? I mean, the main thing is, hey, look, we got a formula relative to M. The useful thing is in the context of paving matroids. So here's our result for paving matroids. And so we're able to relate the Ehrhart polynomial of the paving matroid to the Ehrhart polynomial of the uniform matroid minus a similar term times the number of hyperplanes of size S. So it's the same thing with the Kazhdan-Lusztig polynomial. What's the value of this? So just looking at it, you know, at least the Kazhdan-Lusztig polynomial had this combinatorial feel to it. This is just kind of like, what do we use this for? Well, actually, the Ehrhart polynomial for uniform matroids has been computed explicitly. So what this allows you to do at the very least is it gives you a way to quickly compute the Ehrhart polynomial for various matroids. And so if you have conjectures or you have ideas that you would like to test, paving matroids are a fairly large class of matroids. I know I said they're conjecturally at almost all, but they're known to be a large class asymptotically. Like that's true. And so this at least gives you a way of quickly computing the Ehrhart polynomial in that specific case. And so that can be nice for testing conjectures. Okay, and that's everything I wanted to share about my work with valuations, specifically with Ehrhart polynomials and Kazhdan-Lusztig polynomials. So thanks.
Great. Thank you so much. Let's all thank our speaker. All right. Does anyone have any questions for George?